All right, guys, welcome back for week number 2 of the zombie apocalypse. Okay, so I'm still working with some calculus with exponentials, and obviously anytime you're talking about exponentials, Euler's number comes into play. So I want to take a look at some problems like this, actually some pretty cool problems. So if we take a look at this top one, the first thing that jumps off the page at me is I'm thinking about distributing that division by the denominator, okay? And so if we go that route, so I would get e to the x over e to the 3x dx plus the integral of 1 over e to the 3x dx, like this. Okay, so there's not much you can do here, but there is some simplification here, okay, because obviously the bases in the numerator and denominator are exactly the same, so we could subtract the exponents. So this first guy right here would be the same as the integral of 1 over e, 3x minus x is 2x, and that goes down below, dx, plus the integral of 1 over e to the 3x dx. Now, if I take each of these guys separately, I could use some simple u substitution, okay? So let's see, what do I want to do next? How about we get these guys out of the denominator? And so that first guy would be the same as the integral of e to the negative 2x dx. And this guy would be the integral of e to the negative 3x dx. Okay, so now we can use some simple u substitution. So with this guy right here, if I let u equal negative 2x, then my du ends up being negative 2 dx. So I get negative 1/2 du equals my dx. Okay, so here u is negative 2x, but now over here, dealing with these guys, remember these are two separate problems. Okay, my u would be negative 3x. So my du is negative 3 dx, so I get negative 1/3 du equals dx. Okay, so we go ahead and use our u substitution. So let's see, this would be e to the uth, and where obviously u is negative 2x. So e to the uth, and then I get negative 1/2 du. This guy right here, my u is negative 3x, so this would be the integral of e to the uth. That would be negative 1/3 du. Okay, so let's see. If I take this guy, and remember this u here is different than that u here, and then we bring that down here. Okay, so I take that negative 1/2 and put it out front as a constant multiplier. And then when we integrate e to the u du, we just get e to the u. Over here, I do the same thing. I bring that negative 1/3 out front as a constant multiplier. And then when we integrate e to the u du, we just get e to the u. Okay. All right, now remember, these two u's are different. Okay, so when you go back and substitute in, let's see, this guy, I'm using u is negative 2x, so this is negative 1/2 e to the negative 2x power, and then it'd just be minus 1/3. E to this u right here is negative 3x plus c. Now, I would imagine there would be some people that would say that is an okay answer. And just leave it that way. But of course, I don't really like those negative exponents, so I would probably get rid of them. So I would probably write my answer as -1 over, that would be 2e to the 2x power minus 1 over 3e to the 3x power plus c. I like that guy better. Okay, but again, it doesn't really make any difference. This is acceptable. Okay, I just think that one's a little bit cleaner looking because we get rid of the negative exponents. Okay, all right, first one's down. Let's see what's going on with this second one. Okay, take this guy right here. Okay, so there's no way to really, well, I mean, you could. You could distribute the division by the denominator, but I don't think it's going to help you out. I think it's going to make life even tougher. So I'm thinking, why not let u be the denominator? And if we're lucky, du gives us the numerator. Okay, that might work. So how about we go after this guy? Let's see what's going on. All right, so I got e to the x plus e to the negative x over e to the x minus e to the negative x dx. And once again, I'm going to say, okay, let's see what happens if I let u be that denominator. E to the x minus e to the negative x. Okay, so let's see my du. When we take the derivative of the x, we just get e to the x. Okay, e to the x minus. All right, now this guy right here, notice that it's not x, it's negative x, so I have to use the chain rule. So we get e to the negative x times the derivative of negative x, which is -1. And then if I clean that up, I'm going to get e to the x, these negatives cancel each other off, plus e to the negative x, and we lucked out. Okay, because notice that du is equal to the numerator with the dx. Okay, so when we do our substitution, this guy right here, the numerator and the dx, takes care of your du, and so this is just your u, so we get 1 over u times du. Okay. All right, well, let's see. When we integrate 1 over u du, we get the natural log of u plus c. Okay, so this gives us the natural log of u plus c, and then we go back in and substitute. Okay, so we go back to our u, so we get the natural log of e to the x minus e to the negative x plus c. All right, now, once again, some people would say that's an acceptable answer. I would agree with them because I played around with this a little bit to see what else we could do with it. And there is some things you can mess around with, okay, but it doesn't really make it all that much more simpler. I know, me personally, I'm looking at that and I'm thinking, okay, we know the natural log of e is 1, so can we do something with this? So the first thing I thought of is, let me combine these two guys, okay, into one fraction. Okay, so that would be the natural log of, let's see, that would be e to the x minus 1 over e to the x, like that. And so your common denominator is e to the x. So we get the natural log of, we know e to the x goes down below. So here I'd have to multiply above and below by e to the x power. So when I go e to the x times e to the x, I get e to the 2x minus 1, like this. Now, here's the reason why I was taking a look at that, because now notice we have a log of a quotient, so I can use the quotient rule. So we take the natural log of the numerator, e to the 2x minus 1, minus the natural log of the denominator, which would be e to the x. Okay, so let's see, there's not much I can really do here, e to the 2x minus 1, but right here, if I bring that x out front, I get x times the natural log of e, and the natural log of e is just 1, so I just get x. and then I look at that form of the answer. Oh, don't forget my plus c. And I say to myself, okay, that's another acceptable form of the answer, but if we look at these two, is one really that much simpler than the other? Not really. Okay, I would even be okay. I think that if somebody decided to go here, okay, and then go to here, and maybe even this guy is an acceptable form of the answer. So you have a number of different acceptable forms there. Pretty cool problem. Okay, all right, let's get to that third guy. Okay, this one's, again, a little bit different than the other two. Okay, going back, if we let u end up being this radicand, okay, then when I take the derivative here, I'm going to get derivative of 1 is 0. The derivative here, I'm going to get minus e to the 2x times 2. So when I take the derivative here, I'm going to get 2e to the, or negative 2e to the 2x. And that really doesn't help me out a lot. Okay, so I got to think there's got to be some other way to do it. So remember, this guy looks really similar to some of these guys right here. And so I say, okay, can I get it into one of these forms? Okay, let me see what I can do here. Okay, so let's take this radicand and play around with it a little bit. E to the x, okay, square root of 1 minus, well, e to the 2x is the second power of e to the x. So that's the same as e to the x squared dx. And then you say, okay, well, going back here, can I do something here? Well, how about if we let u be e to the x? Then du is e to the x dx. So that'll take care of the numerator and the dx. Okay, and then I would have 1 over the square root of 1 minus u squared. That guy's right here. Okay, we should be in good shape. Okay, so let's try that. So let's see, if I let u equal e to the x, then my du is equal to e to the x dx. Okay, and that takes care, my du takes care of the numerator and the dx. So I'm going to get the integral of 1 over the square root of 1 minus u squared du. Okay, and then if we go back here, I'm pretty sure it's that top one, where notice we have our u and we have our a equals just 1. Okay, so right down here, your a equals 1. Okay, so we should be able to just apply this. Okay, so let's see. I'm going to get the arc sine, okay, of u over a, which is 1, plus c. So going back and just substituting, I'm going to get the arc sine of e to the x over 1, which is e to the x, plus c. And we're in good shape. Okay, I like that guy. Okay? All right, that takes care of those guys. Let's see what else we got going on here. Okay, you guys had, I think there was one problem. They sort of applied this rule last week. You guys all did a pretty good job of it on the quiz. Okay, we've been doing this forever. Okay, this guy up above. And notice that this works for any real number n. Okay, but what if x wasn't just x? What if it was some, I don't know, some quantity, okay, some u? You know, how do you do that? How do you deal with that? Okay, so just applying the chain rule, if we're going to take the derivative here, so we would just treat this quantity, whatever u is, just like it's an x. So we would just apply the power rule and just bring your n out front, okay, and then subtract 1 from n, and then multiply by the derivative of whatever u is. Okay, and obviously up here, if you multiply by the derivative of x, you just get dx dx with just 1. So technically, the chain rule is being applied up here. We just don't normally see it. Okay, so let's see what we can do here. Now remember, this only works, okay, if that n is an actual number, a constant, okay? And then obviously a variable only shows up down in your base. Okay, remember, if there's a variable in both of them, okay, then you can't apply this rule. You got to pull them apart. Okay, so it's the same thing here. N has to be a number, a constant. Okay, U could be any quantity whatsoever. Okay, so let's see what's going on here, and let's see how easy some of these guys are. Okay, some of them are easy and some of them are a little bit tougher, but none of them are hard. Okay, so let's see this first guy. Okay, we're taking the derivative, okay, of negative 2x to the power of the square root of 21, like that. Okay, all right, so let's see. Well, negative 2 is just a constant multiplier, so we just pull that out front. That's nothing. And so I'm just dealing with x to the power of the square root of 21. Well, x is just x, it's not a quantity, so that means I can just apply this top guy right here. I don't have to worry about applying the chain rule. Okay, so let's see. We bring the radical 21 out front times x to the radical 21 minus 1 power. Okay, all right, so let's see. What's going to be the easy way to do this? I mean, you could leave it the way it is. It's just, I want to make sure that we separate this guy so nobody thinks that goes underneath as part of the radicand. Technically, I could put this out front. It just gets ugly. So we'll take it a couple different forms of the answer. So maybe we just leave it the way it is. And then I would just separate this. X to the power of radical 21 minus 1. Okay, that's one way to do it. Somebody could say, okay, well, let's do something like this. Let's go, I mean, like I said, this is perfectly acceptable. There's nothing wrong with that. Okay, somebody might say, well, let's take this x to this power and put it out front so we don't have to worry about separating it from this radical. And so we would get negative 2x to the power of radical 21 minus 1 times the square root of 21. Somebody might go that route, and that would be okay as well. Okay, but it's just kind of an ugly looking number to begin with. So either one, we're in good shape. All right, so let's move down here. Okay, the second one. Okay, so we're going to take d dx, okay, of 1/8, okay, x to the 4 pi power. Okay. All right, so let's see what we got going on. Well, the 1/8 is just a constant multiplier, so that guy just stays out front. Okay, now, again, x is not a quantity, it's just a variable, and 4 pi is a constant, so we can go right back again, okay, to our top row. We don't have to worry about the chain rule here. Okay, so let's see. So I take the 4 pi, move it out front, 4 pi times x to the 4 pi minus 1 power. Okay, so let's see what we can do with this. Well, let's see. Obviously, the 4 pi cancels with the 8, so we would end up with pi over 2. Okay, so we could write this as pi over 2 times x to the 4 pi minus first power. Somebody could leave it in that form. I don't think there's anything wrong with that. Okay, so let's see. What else could we do? We could put it all as one big fraction. So I could just write it as pi x to the 4 pi minus 1 power all over 2. You could write it like that. Okay. Either way, I think is fine. Okay. I don't think one is better than the other. Okay. So we're good there. Let's see what's going on with this guy. Okay. So this third one down. Okay. We're taking the derivative of cotangent of x to the 3 pi power. Okay, so let's see. Okay, so this guy is a little bit different. Okay, the reason is, notice that our x now has become this quantity. Okay, so now we are going to have to go here and apply the chain rule. Okay, like this. Okay, because your u, or your x, whatever you want to call it, is now some sort of quantity. Okay, so when we take the derivative, we let this be our u, so I get 3 pi times our u, okay, cotangent of x to the 3 pi minus first power. Okay, and then we say, okay, well, let's see, I have to go times the derivative, okay, of u, okay, times the derivative of u, cotangent of x. Okay, all right, so let's see what we got going on. Okay, 3 pi times the cotangent of x to the 3 pi minus first power times the derivative of cotangent. Let's see. Cosecant, I think it's, if I remember right, the opposite of the cosecant squared of x. Okay? You know, I probably ought to check on that because that's one that we don't see on a regular basis. So let me go check on that guy to make sure. I'm pretty sure. So let me pause this video for a second.